Okay, so I guess now's a pretty good time to start as people are slowly starting to show up. People who were at lecture last Thursday noticed that we kind of shift gears in this class. So right now we're doing some statistical mechanics, and the idea is to give a rigorous setting for discussing the idea of entropy. And so what we've been doing is looking at the number of ways to arrange energy in a system. And that's so what we've been doing is computing the multiplicity of possible states of some systems. And the first system we looked at was a binary spin system. Well, why did we pick the binary spin system? So this is like n things that have two possible states. And with spin, it's like spin up or spin down. And just because it's easy. It's the only reason for starting with a binary system. And so what we did is we computed this function, which tells you the number of ways you can arrange the system. And so it's n spins, and s is the distance away from having exactly equal numbers of spin ups and spin downs. And so the number of spin ups is n over 2 minus s. And you can call 2s the spin excess. That's the difference between n up and n down. And that often gives you the total energy of the system, because if you, say, put the spin system under a magnetic field, the spin up would have a different energy than a spin down, depending upon which way the magnetic field is oriented. So we computed this, and it's n factorial over n up factorial and down factorial. And then we used, in the limit of large numbers, we used Stirling's approximation, which is approximation for factorial, to show that you could rewrite this to make it look like this. And this is a Gaussian function. That's a function of the this s number, which tells you how far away you are from 50-50. And sometimes it's easy to write this. So this is when s is 0, you get the maximum of the Gaussian, and then it looks like a Gaussian. And so the thing that I was trying to show you right at the end of lecture is to look at the shape of this as n gets big. And so the maximum it can go, so s can go to n over 2. So if we plot s over n, then it can go to 1/2 to minus 1/2, and then this is 0. And so if n isn't very big, then, so let's make the top here be g of 0. That's s. It's actually n. Maybe what I should call this is n0. That's with s being 0 in there, which is just gives you the peak value. So if I normalize all of them divided by g0, then they have to reach the top, and they have to reach the end here. And so your choices are things that look like this and things that do this. And and so, but as n gets bigger, this gets really, really skinny. And so the width of the Gaussian, when you normalize it by n, winds up incredibly skinny. And so the point is that you just get a huge number more states possible, and it's really unlikely to be far away from that if you have a large number of particles. And so this example shows you that whenever you have big systems, they're really likely to be in the most likely the probability is very high that they'll be near the most likely setting, because the probability distributions wind up so high and so narrow. And so that's one of the assumptions for thermodynamics, is that you assume that it's in this maximum probability situation. So just because the probabilities are so steep. Okay, so that's what we had done, finishing at the last time. So I guess we can look here so having this Gaussian here, you can ask things like, how far over do you need to go to get halfway down? And so in order to do that, you just take the log of this and set it to be half. So we could do that. So I can do that. If I take the log of this thing, it's minus 2s squared over n is equal to the log of, no, it's just equal to minus ln 2. Wait, what did I mean? Yeah, so if I set, let's be specific. What do I mean? Let's set e to the minus 2s squared over n equal a half. Then I can take the log of both sides, and I get this is equal to ln of 2. And now we can figure out what s gives you that. And so it's minus ln of 2. And so we get s is equal to s. So let's solve this. S is equal to ln of 2, divide by 2, and I multiply by n, and then s. So this is of order 1, ln of 2 divided by 2 of n. So s, now I divide both sides by n. S over n is approximately the square root, 1 over the square root of n. And that tells you that the width, when you divide by the total number of possibilities, the width keeps shrinking. So that's kind of another way to show that same concept. Okay, so that's binary spin systems. So let's now talk about another type of system. And again, we're going to look at multiplicity of states. And so this time we'll talk about harmonic oscillators. So a system of harmonic oscillators. And these are quantum harmonic oscillators, so the energy levels are quantized. So let me remind you what a harmonic oscillator looked like. So you quantize it, and it has a ladder spectrum. So the energy, so we have a 0 state, a 1 state. So we label the energy states by the quantum numbers. And En is equal to the ground state plus n h bar omega. So the distance between each of these states is h bar omega, where this is some frequency in the system. So like molecules, vibrational spectrum molecules are described by this. So each energy state is separated by this particular quantum energy distance, right? So why do we talk about, why we pick quantum harmonic oscillators? Well, the fact that the energy levels are easy to write down makes it simple. But so that's a good reason. It's not too complicated. But the other reason for picking harmonic oscillators is actually a lot of physics based around assuming things are like harmonic oscillators. So an example is solids with phonon spectra. Another example is a cavity with photons in it. You can think of photons as being harmonic oscillator states. So so things like the specific heat of solids, you can describe with the system of harmonic oscillators. So that's an Einstein description for a solid. And then for photons, the statistical properties of photons, when you can try and derive the black body spectrum. So that's the Planck radiation curve. And that is also done with like counting harmonic oscillator states. So it's so you see it all over statistical mechanics. So that's a reason why we care about the harmonic oscillator. So yeah, so here are the energy states. So I'm going to say we have, so maybe I should use a different symbol here. I, like that. So I is an integer. And if I is 0, you get the ground state. So those are the energy levels. So what we want is we want the multiplicity function. Multiplicity function. So we have for n harmonic oscillators. And I'm going to give them n quanta of energy. So yeah, so if I have all n harmonic oscillators and they're all in the ground state, then the total energy is just the sum of E0, which is n E0. So this is if all in the ground state. The energy, so this is what we're going to do. Multiplicity. So we want G n of n. So big N of little n. Now if I have n little n quanta, I have to figure out some of the oscillators that you get some quanta, some of the others may not get quanta, but it's total, the total is n. But since I can only, energy states only increase by h bar omega, so the quanta are units of h bar omega. So these quanta are values, are each one, the total number of energy I'm adding to the system is n h bar omega. And so the total energy when I do that is going to be the ground numbers, the number of oscillators times the total energy, the energy for each one being in the ground state, plus n h bar omega. So once I tell you how many quanta I'm going to distribute around, I know the total energy of the system. So that's relevant. We'll see, like when we were talking about binary spin states, we were relating energy to whether it was spin up or spin down. And here it's just got to do with how many quanta I'm going to give the system. Okay, so let's write this up here again. So this is this thing that we're trying to figure out. So let's do an example first. So to get a feeling for how we're going to count things is multiplicity. And then I'm going to derive a formula for it using partitions of integers. Yeah, so let's start with 2 harmonic oscillators and 2 quanta of energy. So, and now I'll draw my 2 harmonic oscillators. This is what they look like. So I can give all the energy to one of them. So it's so if this is the ground state, that's the first state, and that's the second state. That means the other one has to be in the ground state. So that's one way I can give 2 oscillators 2 quanta of energy. Another way I can do it is I can just reverse these. So I can give this guy none, and I can give the other one 2. So this is 2 and 0, and this is 0 and 2. And now let's do the third one. The third possibility to kind of get this idea. I can give the first one 1 quanta and the second one 2 quanta. And so G of 2, 2, there are 3 possible ways to do this. So my multiplicity function is 3. So that's one example. So there's a little bit of subtlety here. So this is not exactly the same thing as how do I distribute 2 things randomly in 2 bins? Because, you know, if I have like a red ball and a blue ball, I can put them both in one bin, or I can put them both in the other bin. But then there are 2 ways to I can put the red one in the first bin, or the blue one in the first bin. So there are 2 ways to do this. So there's 4 possibilities in that situation. But this, we're only counting these 3. So there is a subtlety in how we've decided how to count the states. So this is even though if we had non-identical things that we were distributing, this would be 2 states, but here it's only 1. So we're assuming that the quanta are interchangeable, so we don't care about which one goes where. Okay, so that was one example. So let's do another example of how this works. So let's say I have three oscillators, and I'm going to distribute how many quanta? 4 quanta. So 4 quanta. So this is going to involve some more pictures. So, so I can give follow-ups like I did the last time. So I have to have 5 states here, 0, 1, 2, 3, 4. Yeah, so that's 5 states. So I can give them all to the first one. And then the other 2 have to be down at the ground state. So this is 4, 0, 0. But I can give them all to this one, so it's 0, 4, 0. And I can give them all to the last one, 0, 0, 4. So there are 3 ways to give 4 to 1 oscillator. Okay. So now I want to say let's give 3 of them to 1 oscillator. So let's give 3 to 1 oscillator. And that means I have 1 left, and so I have to give 1 to one of the other guys. So how many ways are there to have 3 given 1 oscillator? So that's 3, 1, 0. I can do 3, 0, 1. Then I can do 1, 3, 0. And I can do 0, 3, 1. And then there's another one like this. So it's 0. Let's do 1, 0, 3 and 0, 1, 3. So I have 6 ways. So 6 ways to give 3 to 1 and 1 to 1. So that's 6. Then now what if I give some 2? So right. So if I can give this one 2 and this one 2 and the last one 0. So there are 3 ways to do that, because I can put that 0 in any of the places. So I can do it 0, 2, 2. So there are 3 ways to do that. Then what if I give 2 to 1 and 1 to the last 2? So I have 2, 1, 1. Well, I just have to count 3 ways to distribute that. So to put the 2, so that's 1, 2, 1, or it's 1, 1, 2. And so there's 6 ways to give 1, 2. One of them 2. If I count these all as those 6. And so if I add these all up, then it's 6 plus 6 is 12, 15. So the total is 15. So that kind of gives you an example of how you calculate these, or if you wanted to draw pictures and do the counting. So n is 3, little n is 4, is 15. Okay. So those are like by hand examples. So now let's generalize a little bit more and count them. Yeah, so let's do examples where we could have n. We'll just use n, big N and little n. But now we'll start with little n being, or let's see. Yeah, so let's start with big N being 1, and then we'll do big N be 2, and then big N be 3, and we'll consider all the cases for that to get some understanding of how we need to calculate this. Okay, so let's take n equals 1. So that's the number of oscillators, and then this is the number of quanta. And so we want to calculate 1n. Well, there's only 1 oscillator, so it gets all the energy. So that means this has to be 1. There's only 1 possible state. So the multiplicity of that is 1. Okay, so what if we have 2 oscillators? And again, we have n quanta. So so let's think about how many ways can I give the first one quanta. So I can give the first one 0 quanta, I can give the first one 1 quanta, all the way up to n quanta. So if I count to 0, this is n plus 1 possibilities. Once I've decided how much energy the first oscillator gets, then because I've said there's a total of n, that means I know how much the second one gets, because it's just so if I refer to S1 as the number that the first one got, then S2 has to equal n minus S1, because the total number, remember, the total number of quanta is n. So if Si is the number of quanta that the ith oscillator gets, then we require that the sum over Si is little n. And so that's why this is true. So because there's n plus 1 ways to choose the number of quanta that the first oscillator gets, g of 2n has to equal n plus 1. So I guess I can store that somewhere. G of 1n is 1. G of 2n is equal to n plus 1. Okay, so we can take this one further and say, what if n is 3? N is 3. So that's the number of oscillators and n quanta. Okay, so how many ways can we distribute? Well, so we can choose how much energy the first one gets. So the first one, you can have 0 all the way up to n, so there are n plus 1 possibilities for S1. But now how much energy do I have left? So the amount of energy I have left is this. And so the second one can get S2. So S2 can be 0, 1, all the way up to this. And then S3 is determined. So there's no ways to choose S3 once I've picked S1 and I've picked S2. So what I need to do is sum over all possible values for S1 and then figure out how many there are left, which is n minus S1 plus 1. So there's n minus S1 plus 1 possibilities for S2 once I've chosen S1. And so I have to sum over all possible ways to choose S1 and then add this together for each one. And then I have to worry about S3 because it's determined. And so if I do that, so I can write this down as it's the sum of S1 equals 0 to n of n plus 1, because that's the number of possible ways to choose S1. And then I have n minus S1 minus 1, no, plus 1. So if I do that sum over this index, then what you get is n plus 2, n plus 1 over 2. And so G of 3, so this is 3 oscillators, is going to be that, n plus 2, n plus 1 over 2, like this. So it's not obvious what the pattern is going to be, right? But these kind of examples start you thinking about how you would come up with a general formula for this. And so now I'm just going to write down the answer, and then we're going to derive it. So I'm not just going to break down the answer and say you could derive it. We're going to write it down, and then we'll show how you could derive it. So the actual answer is this. Oops. looks like this: n plus n minus 1 factorial over n factorial n minus 1 factorial. Okay, so that's what it is. And so this a trick to deriving it. And the trick to deriving it is that you have to kind of realize that we're looking for the numbers of ways to add up integers to equal n. And so really what I'm trying to do is find the number of unordered ways. So that means we don't care about which, if I have a set of integers. So it's going to be a set of integers. I need, how many integers do I need? I need big N integers. I don't care what order they're in, such that they all sum up to n. So it's the number of unordered ways to find n integers that sum to little n. And this has a fancy name in combinatorics, and it's called a partition. And an integer partition is what it's called. So if you're curious, you can look up, what in combinatorics or number theory, a number of ways to make integer partitions. So that's what we want, and now we need to figure out ways to compute it. And so there's a trick to computing it that we using sums, and the problem is equivalent. So if I take a function that looks like this, 1 plus x squared x to the n, and I take it to the nth power, and I expand the whole thing out, and I want to know what's the coefficient of x to the n in this polynomial expanded out. So x to the n, I could take it with 1, and I could take x times x to the n minus 1. That would also give me the coefficient. And so since there are n plus 1 of these, it tells me if I count the number of possible ways I can assign, the coefficient turns out to be the partition. And so if I can compute, when I have a polynomial like this and I expand it out, if I figure out what the coefficient is after I've expanded out, it's actually equivalent to this solving this problem where you want to know the number of ways to do it, because the number of ways comes out in this different ways of adding up x's to get the right coefficient. So each one of these has to sum to n, and there's 0, 1, 2, there's all possibilities. So this is x to the 0, x to the 1. All the exponents add, and they all have to sum to n. So it is equivalent to the number of ways of unordered integers adding to n. So yeah, so I guess we could do a little example and show that it kind of works. So before we computed g of 2, we computed g of 2, 2, and we found that it was 3. So this is 2 oscillators, 2 quantums, gave us 3. And so if this multiplicity thing really is the coefficient of the nth, so let's do 1 plus x squared to the squared, and we'll sum this out for so this is n equals, little n equals 2 and big N equals 2, which is what we computed by doing the possibilities here. So this is 1. I can take this one squared. I can take that one squared. Then I can expand both of these together, multiply these two together. But there are 2 ways to do that, and then there's 2 ways to do this. Yeah, and there's 2 ways to do this, plus 2x squared. And so I have 2 coefficients with x squared in it. So the coefficient with x squared is 3, and that's equivalent to that. So we can kind of see that this idea works. And so now our problem is we want to actually compute. So this was an example that shows that it's reasonable, and we could check more cases to make sure that that's true. So now our problem is we want to actually figure out what the coefficient is on the nth polynomial term. So let's get a little bit more room here. So I need to outline how I'm going to show you that this is true. So I have this function 1 plus x to the little n to the n, and I want to find the coefficient that has n in this. So since I want the coefficient with the nth one, if I add extra terms inside the sum, they'll all have exponent bigger than little n, and so they are not going to affect my calculation of the coefficient that goes in front of the x to the n. So I could, instead of using this function, I could use this function to do the same computation all the way to infinity. So let's write this out in terms of the sum x to the I, and the sum goes from I equals 0 to infinity. So and I can compute the coefficient of x to the n in this, and it'll be the same as the coefficient of x to the n of that, because these higher order terms won't influence the that particular coefficient. So we're going to use this function instead. So I can write g of x. So once I've done the sum out, I can also write it as I equals 0 to, well, let's write it as n, not I, to infinity of g n x to the n. Okay, so this is just saying I want the coefficient of x to the n, but if I have some sum that goes to infinity, I've expanded it all out, I get all possible ones, as long as I pick the power. So this is another way to write this out. So this thing, what I'm going to do now is take the derivative of this thing a bunch of times. So I'm going to take the nth derivative of this. When you take the nth derivative of it, the n term is now a constant. And if I set x to equal 0, that's all that's left. And so if I take the derivative n times, then I can get the one that I want to compute. So I'm going to do that twice, and I'll do it in this form, and I'll do it in that form, and then I'll set the two to be the same thing, and that will let me solve for this function. So we have one more trick, and that's you need to know that the sum of t to the I is a geometric series, which is this. So that's what's inside the sum. So we could write this as 1 over 1 minus x to the n, using that geometric series. So this geometric series is useful, and it's also useful in the problem set. So if you're not familiar with how to derive it, I think I gave it as an example in the workshops. You can figure out how to derive it. It doesn't converge unless t is less than 1, but so this is just this useful thing to have here. Okay, so now I have a formula for this, and I need to know what the coefficient of x to the n is for this. And I need to know what, so I'm going to take the derivative n times of this, I'm going to take the derivative n times of that, and then I'm going to set them equal to 0. So let's start with this one. So g of x is 1 over 1 minus x to the n. And so let's take some derivatives, dg of x dx, and I have an n, and then I have 1 over 1 minus x to the n minus 1. Wait, that's not right. It's n plus 1, right? And the minus sign goes away because there's a minus x there. And now I can take the second derivative of it. And I have n, and I have n plus 1, 1 minus x to the n plus 2. And we can keep doing this. And so in general, dn to the little n of g dx to the n is going to be n times n plus 1, because I do it n times, n plus 1 over x, 1 minus x to the n minus n. Because we've taken in, actually, it should be n plus n, right? There's a mistake there. What's that? Right, because we've taken n derivatives. So now let's set this to be 0. And then this just goes away. So we don't really need to worry about it. Which is good. So this is a, it's a product series, but I can also write this as n plus 1 factorial divided by n minus 1, I think. Okay, this is a minus 1 here. N minus 1 factorial. So I just have to extend this to 0 and then divide off by what it is, and that's what that part is. So this gives us one thing that we need to know. So let's write that at the top. dn of g to the dx to the n at x equals 0 using this is n plus n minus 1 factorial divided by n minus 1 factorial. Good. So let's remember that. So that's the first time we're taking little n derivatives. The second time we're taking n derivatives, we're going to use this form of it. So let's take n derivatives of this form of it. And it's going to be g, it's a sum actually, sum of n equals 0 to infinity of g and n. Now I just need to take, actually if I'm taking n derivatives, let's rewrite this different index. Like that. So I write, so since I'm taking n derivatives, it's n times n minus 1 times n minus 2, all etc. x to the I minus n, because there's n derivatives. And now if I'm going to set this x equals 0, all of the terms drop out except for the one that we want, where I is equal to n. And so, and this turns into n factorial, and so we get n factorial g of n. So x equals 0. So now I said this equal to that, and the answer is exactly what we wanted. G of n equals n plus n minus 1 factorial over n minus 1 factorial n factorial. So that was kind of a, partition number combinatorics example. It's mainly for entertainment, actually, but it shows you it's not hugely difficult to derive. It takes I would say it's better if you read through it a couple times and follow the steps. I'm pretty much following the proof that was done in Kittel, but I've actually added more steps to make it hopefully so that I can follow it, make it a little bit more clear. And if you're interested, read up on partitions. So I gave a few links to some math sites that explain what partitions are a little bit more detail. So, right, so we have a formula and now we can use it in various settings. And the harmonic oscillators, this set of n harmonic oscillators is actually kind of nice. It's one of the nice simple examples, simpler, I wouldn't necessarily call it all that trivial, but simpler examples that people use in statistical mechanics to explore things in a way that you can calculate the actual state. So this thing, you could take a couple hundred harmonic oscillators and actually look at what the multiplicity functions are without, actually computing numbers and see what the entropy looks like. So remember, entropy is the log of this. And so if you want to calculate some small numbers of oscillators, exactly you can. It's a nice closed form thing. So I've been kind of sloppy about the ground states in this example. And so I did keep track of them in the beginning, but we really add quanta on top of the ground states. So the ground state, again, one more warning, the ground states energies will become important later on in statistical mechanics when we look at the Boltzmann factor. So that's just something to keep in mind. Okay, so all right, good. So let's move on to temperature. So we spent some time figuring about how to calculate multiplicities of states. And there are two web work examples where I'd ask you to use those factorial functions so that you understand what they are. So what's the problem? So we have two systems. So here they are. So I guess this example I've done with the binary spin system. So these are two binary spin systems. So the first system has n1 things, n1 spins. That's the number. Then the second one has n2. And then I need to tell you the number of spin ups that would be in the first system. We can define that with this S parameter, which is the number of downs past n/2. And S2 is the number for the second system. So now we're going to put these two systems. So the total, I can also combine these systems and describe them in terms of a total. And then the total of spin downs past the half mark would be that. You just add them. So we have two binary spin systems right next to each other. We can also think about them as a single huge system. So now we're going to do we're going to put a thermal contact right next, so they can exchange energy. So what's meant by a thermal contact? They can exchange energy. So energy is set by this S parameter because it tells you how many spin ups versus spin downs you have. And so that means some spins on one side will flip down, say, and then a couple on the other side have to go up in order to equalize the total energy. So the whole system we're going to make the whole system be isolated. So no energy is allowed to go into the whole system. So the total energy, which is set by this S, is fixed. So big N is fixed. This S is fixed. So what's fixed? N1, N2, N, and S are fixed. But S1 and S2 aren't fixed, but S1 plus S2 is fixed. So that's what's meant by this two systems in thermal contact, so they can exchange energy. So what's the multiplicity of the first system? So the multiplicity of the first system, I spelled wrong. Multiplicity. So we can have a G1 and a G2. Those are the multiplicities. So G1 of N1 S1 and G2 of N2 S2. And we could also have a full multiplicity function that's N of S if we think about it as a combined system. So so this thing, if I specify that I have S1 in this subsystem, and I have S2 in this subsystem, so this is the multiplicity states of this one. For each of these, I could have one of those, or I could have any of these. And so the total multiplicity is actually just the product of these. So given S1 and S2, this is true. So that's the total multiplicity of the system. So so before we showed for the binary spin system, it was convenient to write these multiplicity functions like this. So if we have G of N of S, we could write it as a G of 0 e to the minus S2S squared over N. We did an approximation where we showed you could make it look like a Gaussian using Stirling's approximation. So we can do that for each of these two. And so let's take the log ln of G is the log. So each one of these can be written out with this exponential. So it can be ln of G1 of 0 and G2 of 0 e to the minus 2S1 over N1. So these are squareds, minus 2S2 squared over N2. And so this is the log of all of this. And so I can write this as ln of G1 of 0, G2 of 0, minus 2. So the natural log of an exponential is just the thing, the exponent. So this is S1 squared over N1 minus 2S2 squared over N2. Okay, so this is if we have S1 and S2. But if I fix S2, S1 plus S2, then I can replace S2 with S, total S, minus S1 squared. So S2 is S minus S1 because S is fixed. So so now I have this total system. So this, remember the log of the multiplicity function is the entropy. So now I can ask, where is the entropy maximized? So I can vary S1 and say, which is the number of spins that this part gets, number of spin ups or downs that this one gets, number of spin downs past half. Where does the entropy of the whole thing get maximized? So where's the multiplicity, the peak for the whole system? But now I'm allowing these two to exchange energy so that I achieve that state. So so the assumption is that it's most likely that this whole system is going to be at the peak of the multiplicity function. So if I take the derivative of this with respect to S1, keeping S fixed, N1 fixed, N2 fixed, this constant is going to go away. Then I solve, I can figure out what S1 maximizes the multiplicity. Another way of saying that is it's maximizing the entropy. And the point is, if I take these two systems and they're initially not, they initially have some number of spins and this one, some number of spins in that one, which is equivalent to saying this one has some amount of energy, that one has some amount of energy. I stick them together, now they can exchange energy. The whole system should then go into this maximum entropy state, which is when the multiplicity function or the log of the multiplicity function peaks. And so they'll exchange energy until they're in the most likely setting. So, so that's what we're gonna do. And figure out when that happens. So I can take the derivative of this thing, dln of g, actually it's not a partial really, it's just a derivative, dln g ds1. And so I can take the derivative of that. And it's equal to minus 4 s1 over n1, plus, because there's a minus sign in there, 4s minus s1 over n2. And now I'm going to set it to be 0, and I'll solve for s1. And if I solve for s1, I get s1 over n1 is equal to s minus s1 over n2. And that's equal to s2 over n2. So, and this is for equilibrium state. And now I can solve for the S1 that gives me this condition in terms of S. And so let's say, so now I'm going to figure out, so they're going to exchange energy now, and they're going to be in this maximum entropy state. But that doesn't mean, so that's going to give me a particular value of S1 and a particular value of S2. And so now I can figure out what those are. And I'm going to call them S1 hat and S2 hat. And the number you get, if I just solve this, is this. And S2 hat is equal to the same thing, but with N2 over N. So these are the equilibrium values. So now putting those back into this multiplicity function, we can say, what's the multiplicity function of this maximum entropy state? And so I'm going to call that G max. And so another way of writing that is G1, G2 max, because we can always multiply the two multiplicity functions. And what it turns out to be is this, G1 of 0, G2 of 0, e to the minus 2s squared over n. Not surprisingly, because it should look like that, but you can show that this is what you get if you put those values in when you multiply the two multiplicity functions together. So so we can do things like say, what if we take it very slightly out of equilibrium? So so in that case, what if slightly out of equilibrium? So what do I mean by that? So let's take S1 equal the equilibrium value, and we'll add in a slight number of spins. So it's not quite in equilibrium. Then S2 has to equal S2 hat minus delta. And we can find a formula for that. And in particular, it's useful to put it in units of this maximum value. And so if you do that calculation, what you get is G over G max. So this is if it's slightly out of equilibrium, is equal to E to the minus 4 delta squared. Yeah, over N1. N1. So this, yeah. So now we can, so there's a little bit of calculation involving these exponentials. It's not very exciting calculation though. But so this is what you get. But now we can ask, what if I have, so supposing we have a system of spins with, say, Avogadro's number of spins, and I move it out by, say, 10 to the 12 spins. But 10 to the 12 squared over Avogadro's number is like, so this is 10 to the 12 over 10 to the 22. So let's figure out, so suppose I have 10 to the 12 spins, e to the minus 4 times 10 to the 12 squared, which is 22, and I divided by 10 to the, is that right? I've got it squared. Ten to the 12. Oh, okay. 10 to the 12 squared is 10 to the 24. Okay, that's why. Then that, no wonder. Okay, there's where my mistake. So I take 10 to the 12 squared, I take this, then this turns into e to the 200 or so. Maybe it's 400, e to the minus 400 or so. It's actually e to the minus 400, taking into account that. So this is a really, really small number. And you'd have to go up by quite a bit more in order to, quite a bit less in order to make it not be a small number. And so this is, the fact that you've got this exponential involving some large, some small, some really large thing in the denominator here means that this winds up being big easily. And so it winds up just like dropping very quickly. So it's very, very unlikely that you have very many atoms or spins that are outside of equilibrium, which is why, that are off. So it's very unlikely to be out of equilibrium or much out of equilibrium. And so that's why it's a good assumption to say, once you put these two systems in contact, then they're going to be near the maximum entropy state, which is the most likely state for the system. So that's the point of that example where you actually compute the probabilities. Okay, so so the reason for going to the binary spin system to do this particular example was just that we had this nice exponential form for the multiplicity of states. But we don't necessarily depend upon that. And so what I'm going to do now is discuss a more general system. Just assume we know how to write down the multiplicity of states as a function of energy. And now what we're going to do is ask, what do you need for it to be in equilibrium? And this condition, so let me outline what we're going to do. Again, it comes down to drawing one of these boxes. So again, we have two systems. And if we wanted to calculate example systems, we could, and like say either use a binary spin system or the harmonic oscillator system, because we have nice closed forms for them. So we have N1 particles. Now instead of using S, we'll use U. So, so this system has N particles, has multiplicity G1, N1 particles, multiplicity G1, energy U1. This system has N2 and total energy U2. And I'm going to assume that we can write the multiplicity functions like this. G2, N2, U2, or G of NU. So again, what's fixed? N1, N2, U, which is equal to U1 plus U2. Those are the things that are fixed. And once we put it in thermal contact, the thing should now move to having this optimized. But when you start off, U1 and U2 might not be at the values that give you the maximum multiplicity function. And so energy will be exchanged until it reaches the maximum entropy or maximum multiplicity for the combined system. So I could write G of N1 U is equal to G of N1 U1 plus U2. And this I can also write as G of N1 U1 times G2 of N2 U2. like we did before, because, you know, if I have a multiplicity of states for one of them, for each one of those, I have the total number of multiplicity states for the other one. So the total multiplicity is the product of the two. So now when you put it in thermal contact, it should be at a maximum. So that means dg is going to be 0, but I want to vary the energy in one of them. So I can write this out as dg1, which is of n1 u1. So this I can write as a partial because I'm keeping n1 fixed. So du1, actually usually people write this when n1 is fixed, but so we're taking the derivative with respect to the energy of the first one. So this is a product, so I can multiply by g2. And then n2 u2 d u1, because I took the derivative with respect to u1. Now I can do the same thing, taking, so I took the derivative with respect to this, I can take the derivative with respect to that. So it's dg2 of n2 u2 du2, and I'm keeping n2 fixed. And now I have to multiply by g1 and du2. And at the maximum entropy state, when it's in equilibrium, this is going to be 0. So because energy is conserved, du1 plus du2 is also 0. And so we could convert this derivative into a derivative of u1 with a minus sign, actually. So, so let's do that. du2 is minus du1, and I can rewrite this equation. So let's do it up here so I don't need these anymore. I can rewrite this as g, so I'm going to move this g1 to the other side here. dg1 du1 is equal to 1 over g2 dg2 du2. That's, yeah, so this condition that they're at equilibrium and I flip the sign of this one means this is true. So it helps to remember that d ln x, actually not x, f of x dx is equal to 1 over f of x df dx. Do you remember how to do the chain rule with a natural logarithm? So this is 1 over something times the derivative of something. So I can write this as d du1 of ln g1 is equal to d du2 of ln g2. This is getting why we define entropy as a log too. So the entropy is the log of the multiplicity function. So I can add that to my lists here. And then this gives me d du1 of entropy of 1 is equal to dg2 of entropy of u2. So entropy. This happens at equilibrium. So, and not surprisingly, the derivative of the entropy with respect to energy is going to be our definition of temperature. It's actually 1 over temperature. Because when the system is in equilibrium, meaning no more energy is being transferred between the two halves of our system, that's when they have the same temperature. And so we'll define our temperature in terms of these derivatives. So in particular, so 1 over T, we're going to define it like this. So the definition of temperature. So this is like heavy on the vocabulary, right? So we defined entropy as the log of the multiplicity functions. We have two systems. We bring them together, they exchange energy to maximize the entropy. At that time, this is true, that the derivative of the entropy of the first one is equal to the derivative of the entropy of the second one. So that's the same condition as at equilibrium. So we're defining our energy, our temperature in terms of this derivative. And that way we know that when those two subsystems have the same temperature, they stop exchanging energy. And so that's why the temperature is being defined in this particular way. So, and if we, so here we have entropy as a unitless thing, but if you push the KB inside here, you can define an entropy, an S is equal to KB, this. So this is a conventional entropy. And then again, temperature is the derivative of conventional entropy without the Boltzmann constant in terms of energy, with respect to energy. Okay, so let's rewrite that a whole bunch of times. So this is like the heart of the whole thing, entropy and temperature and multiplicity functions. Okay, so for a system, 1 over t, we can write it as KB d entropy, where this is the log of the multiplicity function, du. I can also write that as ds du, where s is KB this. And remember, this thing is the log of the multiplicity function. And these derivatives right now we're doing with keeping the numbers of particles fixed. So when you start changing that around, you get different kinds of what's called ensembles, where you can look at how other things vary. But here we're only letting energy vary between our two subsystems. So now let's look. So this 1 over t is ds du. So I can write this ds du, right? So not worrying about what I'm keeping. When you write partials, usually it's because we're keeping something fixed. So du is equal to t ds, okay? So if I change the entropy by ds and multiply by temperature, I get the change in energy. So this is a change in energy is TDS. So this is also known as heat. So when you say I'm moving energy from one system to another system because it's going to a maximal entropy state, that's another way of saying you're letting heat being transferred from one system to another. So heat is often given, so there's different ways to change energy. I mean, you can raise a block, for example, potential energy. You can speed it up as kinetic energy. Here we're just talking about thermal energy, which has to do with this distribution of states. So in that setting Q, which is the change in energy, is equal to TDS. So you'll see people say that over and over again, and you'll see this over and over again. So yeah, there's a trivial problem on the web work that just makes you figure this out, right? Just to remind yourself that Q is equal to TDS, and that's the same thing as energy. So yeah, but if you want to actually calculate what entropy is for specific systems, so these like statistical systems that we talk about are settings where we can actually write down closed form solutions. They're closed, analytical equations for entropy. And so they're helpful. Otherwise, what you're just defining entropy and energy and changes in terms of differentials, and you don't really have any closed form things. So that's the nice thing about having these toy models, to keep in mind what's really going on underneath when you say what do I mean by entropy? We don't have any uncertainty right now. It's like multiplicity, log of multiplicity of states. And that's an absolute quantitative definition, which I find very comforting. Okay, we have a little bit of time, so I'll do this more carefully next time probably in Hoyt. We'll see what happens on Thursday. But one thing that's nice. So let me just start drawing a picture because I'll draw it again next week. But supposing we have two systems, and so I think let me try and remember what variable I plotted. Did I plot entropy or did I plot? Yeah, I plotted entropy. And so I have two systems. So again, this is the N1, U1, G1. And I have another system, N2, U2, G2. And I can think about varying the energy in the first one. So as the system has more energy, chances are it's going to have more entropy. Now, if the total energy is fixed, so this is G1, or it's actually ln of G1 because it's the entropy, is equal to sigma 1. The other system, so because the total energy might be fixed, if I give more energy to the first one, I take away energy from the second one. And so the entropy function for the second system, ln G2, which is sigma 2, chances are it's going to look something like that. And here we have this definition. Here, this is in terms of sigma. 1 over temperature is the derivative of the entropy with respect to the energy. So, that's actually, so this is the slope on this plot. And the slope here is equal to the slope with a minus sign there. So the minus sign, you can flip the sign. With derivative of entropy with respect to U1 gives me this one. The derivative of entropy with respect to U1 would give me that one. But in order to do this, I need U2, and so it has the opposite sign. And so the two slopes are actually the same at some particular point. And it may not be where they cross, actually. So let's be a little bit more careful here. So now if I add these two entropies together, that's the same thing as multiplying the multiplicity function. So the total entropy, this is going to be ln of this, looks like that. And at some point, we get the maximum. And the maximum is going to be where the two slopes are the same. So I can also think about this problem. What if I start here and the slopes are like this? They're not equal and opposite, which is the same thing as saying that temperatures are not the same because temperature just depends on the slope. So the system has to go to this maximum point where the two slopes are the same. So if we start off out of equilibrium, once the two systems are put into thermal contact, they'll get into equilibrium. The slopes will become equal and opposite on this plot, and that will be equivalent to saying that it's a maximum entropy state. So remember, when you add entropies, you're multiplying multiplicity functions. So that's why these two curves add. So we'll talk about that a little bit more next time. And I think we're kind of out of time, but does anybody have any questions? We have like a minute or two about this topic of entropy and multiplicity functions.
Could I just see the graph again?
Oh, I'm in front of it?
Yeah, thank you.
Yeah, so it is, all these pictures are better, clearly defined without mistakes, hopefully, in my lecture notes. But yeah, so this particular picture, you can draw it for a specific system. So it's a cartoon, but it's based off of saying, let's say we have 200 quantum harmonic oscillators with n quanta, and we'll give them certain amounts of energy. And you could actually make a specific example. And this particular plot was derived from an example like that. So the shapes are, meant to actually be using, so you, and in the problem set, so the WebWorks this week, I just ask you to look up the multiplicity functions for the spin system and the harmonic oscillator system. And then remember that Q equals TDS. That's it for the third one. For the first problem on the regular part of the homework, I ask you to compute the entropy using one of those formulas for two systems. And then you put them in equilibrium. What's the new entropy? And you're supposed to show them the entropy always goes up. And so if you start off down here, it'll go to there. So that's specifically what that particular problem is. The other problems on the problem set, like the second and third one, they're not meant to be hard, but the thing that makes this particular field hard is there's a lot of vocabulary and setting to absorb. So the calculations should be pretty short once you figure out what you're meant to calculate. So I think most of the time you're going to be spending on this week's homework is figuring out what is entropy, what's the formula, not actually spending much time actually trying to calculate anything. So yeah, so it's a little bit of different style of homework for that reason. So take a look at it, and your workshop should be focusing on what these definitions are, more conceptually what these definitions are, and less on details of doing a line calculation. So just to warn you about that, it's different. So this is quite different than the rest of the term, actually. Which you'll either, probably most people really like it. I really like it. It's really neat. So the statistical mechanics backdrop for physics is fantastically beautiful. So it's like, it's such a lovely explanation for complex phenomena that you base it on these just very, what's the word I'm looking for? Rigorous statistical calculations. It's so much nicer than thinking about entropy as like some nebulous disorder thing, and which you can't really get your hands around. It's like, so the statistical underpinning of thermodynamics is very nice. So take a look. Yeah, it's not trivial to understand the vocabulary in this setting. Temperature is just a derivative of entropy with respect to energy. This is like a nice idea. Any more questions? No more questions? Okay, well, more questions on Thursday. Thursdays are planned to be our last class on campus. Yeah, so last lecture in Hawaii this term. Can't believe we're almost at the end of term. Okay. Bye, everybody.
Thank you.